We are taught that some numbers are real and some numbers are imaginary. But how does something called imaginary become one of the most important ideas in modern science? For centuries, math was built on numbers we understood: positive, negative, zero. But as algebra advanced, mathematicians ran into something that seemed impossible: the square root of a negative number. Back in the 1500s, Raphael Bombelli showed the world these weren't mistakes. They followed their own rules. Descartes gave them a name: imaginary numbers. And Euler gave us the symbol we still use today, I, where I squared equals negative 1. Okay, so what does that actually mean? Consider the square root of negative 4. We can rewrite it as the square root of 4 times the square root of negative 1. The square root of 4? Easy, that's 2. But the square root of negative 1 doesn't exist. Not on the real number line anyway. Which means the square root of negative 4 equals 2i. Oh, so now equations started producing answers with both real numbers and these imaginary ones, like 3 plus 2i, and these became known as complex numbers. But wait, the real number line has no place for them, so mathematicians drew a new line, perpendicular right through 0. This is the complex plane. To plot 3 plus 2i, we move 3 units right along the real axis, then 2 units up parallel to the imaginary axis. From 0, we draw an arrow to the point where we stopped, and that arrow represents 3 plus 2i. But here's where it gets really interesting. Watch what happens when we multiply by I. Now, let's start at 1. Multiply 1 by I. We get I. The arrow moves from 1 to I, a 90-degree rotation. Now multiply I by I. We get I squared, which is negative 1. The arrow rotates another 90 degrees. Next, multiply negative 1 by I. We get negative I. Finally, multiply negative I by I. We get negative I squared. Since I squared is negative 1, this becomes 1. And after 4 steps, it returns to where it started. Now, let that rotation flow smoothly and just focus on the tip of the arrow. Look at that. It moves like simple harmonic motion, which is exactly why complex numbers became the language of electricity, wireless signals, quantum physics, signal processing. Every system we build on waves is underneath a rotation. So, imaginary doesn't mean unreal. It's a hidden dimension of mathematics, one that helps us understand the real one.